Okay, hello everyone. I hope you all had a great day so far. Today, we are gonna talk about the stability in the control system. So far, we talked about how to model a system, either using the transfer function, which is an S domain, using the Laplace transform, or actually try to model a system in a time domain using the state space modeling. So far we covered how to model the system. Now, as you remember in the first chapter, the introduction to control system, we said that one of the most important analysis that we are going to do for our control system is the stability analysis. Okay, because without the stability, it doesn't work to kind of go over the response of a system, because eventually we cannot control the system if it's unstable, and we cannot reduce the errors if we don't have a stable system. Okay, so when we talk about analysis, we said we are going to have transient response, a steady state response, and a stability. And as we mentioned, the stability is baseline for analysis. Otherwise, transient response and steady state response doesn't matter. Okay? Now, we also mentioned before that when we talk about the response of a system, we are going to have two types of system response. One was the force response, which was basically the response of the system when we injecting an input. And the other one was the natural response, which was the response of a system, the internal characteristics of a system, okay, that was based on an initial condition and the topology of our system. Okay, now when we talk about the stability, by stability we are gonna we mean that we are gonna analyze our natural response of a system and see if the natural response of a system is stable or unstable. Okay, now what we mean by stable. Okay, when we talk about a system that is stable, we are talking about a system that first is controllable. But what that means? That means whatever input that we inject into the system, okay, the response of a system, which if you remember was the input plus the natural response toward that input. You remember that? The response of a system is finite, and we can actually measure the response of a system through the time. So whatever situation that happens to the system, we know that the output is going to be finite. And if it's finite, is measurable, and if it's measurable, we cannot control it. We can control it. Okay? Now, we have several types of system when it comes to the stability. One is very obvious, which is a stable system. Okay? When our system eventually reach a certain step as a steady state. You remember when we had like an exponential decay, okay, or exponential result when we had that e to the power of minus at, eventually our system would end up in a finite value defined by the input or initial condition in a force response. Okay, we also talked about the second order system, okay, when beside the decay we had some oscillation. If you remember, when the poles of our system had an imaginary value, so it was a complex number, not only we had a decay, but also we had a certain oscillation. Okay? Now, based on that, we had either a stable system, which is fully decaying response, so we only have the exponential with the power of minus something times t, so we are going to end up the errors or the differentiation from the final value is going to be decaying with an exponential function, okay? Or we can define a marginally stable, okay? When we have oscillation, but that oscillation do not goes away. If you remember, we consider some situation when the poles of a system was two conjugate imaginary number, okay, that fall exactly on the imaginary line. So when that happens, when our S's, okay, are only a constant, which is a real number, then we are gonna basically have a limit of our model when t goes to infinity equal to the steady state value. Let me write that so you don't miss that steady state value. When it was happened, when we had the situation that we had a real number, meaning in a plot that we had for poles, the A, no matter how many A we have, okay, would only happen as a negative real value. Do you remember that? For example, if we had -2 and -1, we knew that f of t is going to be e to the power of -2t plus e to the power of some coefficients is applied -1t. Okay, so eventually at time equal to infinity, we are going to have a plus b, which is a finite value that we consider a steady state value. Are we good? Now, another situation, so we call this part a stable part. So this is a stable. These type of system are stable. Now, another situation that we had in our system was when we had those S's, S1 and S2, as a complex number. So it was alpha plus some J beta, plus minus actually. We had two conjugate number as our poles. Do you remember that for a second order system? So on those situation, these were complex numbers which in the limit of our function at time to infinity, we still reached the steady state value but in a way, before we reached the steady state value, we had some sort of oscillation. So if we had two conjugate poles, our system would have such a behavior, right? This was our response of a system, but still after time, in time infinity, we will reach the final value. which if you remember, the function was e to the power of minus alpha t times a cosine of that beta t plus b sine of that beta t. Remember that function? Because of that e to the power of minus alpha t, we knew although we have oscillation, we would decay to a steady state. Is that clear? So if we decay to a finite value, which is our steady state, that means we are still stable. Now, what would happen if our S1 and S2 were only imaginary number? So it was plus minus j some beta. On that situation, our poles would fall exactly on the imaginary axis. Okay, so we had plus j beta and minus j beta exactly over the imaginary part. If we had such a poles, remember our input function didn't have this exponential, so we only had that a cosine of beta t plus b sine of beta t. You remember that? So in this situation, our response, this is sine and cosine, was always an oscillation. Are we good? Now, this oscillation, because of the characteristic of sine and cosine, which is only varies between -1 and 1, okay, we still have a finite value, although it's oscillate, but the max and mean are finite. So we are oscillating in a specific margin. Are we good? Now, this situation is not fully stable because we have oscillation, but it doesn't increase or go wild, so we call it marginally stable. We still have a controllable system, but we cannot never reach an exact, like one finite value at a steady state. Are we good? Now, let me ask you another question. What would happen if our S1, let me put a minus here, that's better representation. What would happen if our S1 and S2 would have a positive real number plus minus imaginary? What would happen if our alpha here, the real part, is a positive number? Here, our real part in both these situations, our real part is negative number. What would happen if we have such a situation? So that means the S's would fall on the right hand side of our coordinate, the right hand side of our imaginary number. Now, from this formula, you can imagine that the f of t on that situation is going to be e to the power of alpha t, a positive number in a power, times, because it's complex, we have oscillation to cosine of beta t plus b sine of beta t. Now, if beta is 0, simply means we don't have these values. If beta in this function, if beta is equal to 0, that means f of t would be only e to the power of alpha t, because we would only have like a real values. Now, what is the limit? What is the limit that of that f at t goes to infinity? What is the limit of e to the power of alpha t? Alpha is a positive number when time goes to infinity. This is positive. So what would be the power of e? T goes to infinity, so it's alpha infinity, which is infinity. So e to the power of infinity is, e is a constant number. Okay, so it goes to infinity. What that means? That means our response from whatever initial value that we have is gonna go higher and higher. As time passes, the response would increase. Now, we don't have any finite steady state here. So what that means? That means this situation, based on the definition, is unstable. Now, from the graph that we plot for the poles of, for example, the second order system, you can easily have a conclusion that if our poles fall into the right hand side of this plot, so the real number is bigger than 0, not equal, bigger than 0, okay, we have an unstable system. If our poles fall on the left hand, so alpha is less than 0, we reach the stable value. And if it's happened to alpha to become 0, we only have an oscillation, but it's finite, so we have marginally stable system. Are we good? Any questions so far? No? Okay. Now, up until now, when we wanted to find our poles, we simply solve the equation in the denominator of our system, of our transfer function. You remember? So in a S domain, we find the poles of our denominator, and we would have, we solve the denominator for the poles, and we had our situation. Now, what if our denominator is a crazy nth order system? For first order and second order, finding those poles are easy. third order is possible, okay, but it's hard. But when we go to like a fourth, fifth, and nth order, now it's not easy to find the poles and find out if there is any right-hand side poles or not. So how we can deal with that? We have to come up with another method so we will be able to actually analyze the stability of our system. Are we good? Yeah, go on.
Sorry, quick question. For the two state, like for a system to be stable, it could be either have like real numbers or complex numbers.
It could have real number, only real number, or complex number, as long as the real part is a negative value.
Okay.
We are stable.
Oh, okay.
Okay, because we are gonna have an e to the power of minus something,
and then it'll just.
And that e to the power of minus something at t infinity would eventually goes to 1.
Right. Okay.
Does that make sense?
Like as long as it reaches like
to 0,
like a steady value, like towards the when it goes to infinity, then it's stable.
Then we are stable.
Okay.
And if we have a finite oscillation, we don't reach any stable value, a finite value, but we are oscillating around a final value. Okay, then we have marginally stable.
Okay.
Is that good?
Yes, it's still contained, like.
Yeah, it is still with a certain margin. We still are having a finite steady state. But when we have the alpha, the real part, as a positive number, then this exponential become an increasing exponential instead of decaying exponential. That means as time goes by, we are going to have higher and higher value. Now, if you have purely real number, so S1 and S2, this situation is when S1 and S2 are some real numbers, some positive real numbers. And if you have a complex number, so S1 and S2 become a positive number plus minus that J beta, what's happened is that simply you are going to have an oscillation, but as time goes by, that oscillation increases. Instead of here that we had decaying oscillation, now here we have an exponentially increasing oscillation.
And alpha is positive.
Because alpha is positive. So this e to the power of alpha t, as time goes by, would increase. Are we good? All right, okay. Now, I have a quick question before I introduce the a method to easily analyze the higher order system. Okay? And the question is, so far we talked about the poles and we analyzed our system in an S domain. Let's say we have a steady state, okay? And we are in a time domain. We're talking about the differential equation. What merit we can use instead of the poles in an S domain to find out if the system is stable or not? Do you remember? In time domain, in a steady state, we had a specific parameter that we defined that was equivalent of the zeros in S domain, of the poles in S domain. Do you remember what was that?
Zeta.
No, that psi is still in the S domain. Okay? Do you remember the last parameter that we introduced in a time domain analysis? It was the eigenvalues. And we said the eigenvalues are equivalent of those poles in time domain. So if you have a time domain system and you know the eigenvalues would exactly have the same situation as these problems. So if the eigenvalue has a negative real number, we are stable. If it has a positive real number, okay, we are unstable. And if it has a zero real number, so it's fully imaginary, okay, that means we are oscillating. So the eigenvalue is the equivalent of that poles in time domain. That was like a kind of like a side note. Now, are you okay with the writing? I want to erase the board. Are we good? Okay. Now let's see what's gonna happen when we want to like analyze a higher order system. Now, in a stability analysis, we had a method that is named is Routh-Hurwitz. Am I writing it right? Yeah. We have a method named Routh-Hurwitz, which is a shortcut basically when we want to like analyze the stability of a high order system. Let's say we have a first order system. I am gonna use later on this example, like there is some sort of nominator, we don't care about that for stability, and we have A4 S4 plus A3 S3 plus 3 plus A2 S square plus A1S plus A. So this is our transfer function. Okay, we are going to use this as an example, but before that we are going to talk about the general Routh-Hurwitz method. Now let's say in general term we have an nth order system. Our nth order system was ANSN plus AN minus 1 S to the power of n minus 1 all the way to A1S and A0. That was an n order system, and we want to see when it is equal to 0. Okay? Now, Routh-Hurwitz has a table, and it helps us to find out if we have an stability in our system or not. Now, how it works, when you have an nth order system, okay, you are going to start with rows named by each of the nth order. We are going to name them like Sn minus 1 all the way to S, and we are done. Okay, so we are gonna go all the way to S, and not S0 is also a term. Now, when we wanted to like use the Routh-Hurwitz for stability analysis, the first step is to find what is this table, because that's the tool that will help us for stability analysis. Now, in order to draw or to fill out this table, what we are going to do is in Sn row, we are going to list the coefficients of our function, okay, in order that like we write an, we skip the next one, Okay, and the next term is gonna be the after one, so a n minus 2. So we are gonna skip 1 and go to the after that, a n minus 4 all the way. Okay, if we skip all the way through that, we are gonna reach a0. This is gonna be our first row. Okay, let me rewrite that. A n minus 2, a n minus 4, all the way to a0. Now, for the next row, we are gonna do the same, but for the coefficients that we missed, we skip in the first row. So it's gonna be a n minus 1, a n minus 3, a n minus 5, all the way to a1. Are we good? Now, what is gonna be the next situation, next row? We don't have any coefficient left out in our equation. So for the rest of the rows, we are gonna use these terms, okay, in order to calculate the values in a third row. And for example, let's call it the third row, we call it B1, okay? And how to find it is gonna be minus the determinant of the first two, okay? So the determinant of an minus 3, an minus 2, and an minus 1. Let me write it bigger. So I'm gonna write B1, B2, B3, okay? And B1 is the minus determinant of these first two rows, an minus 2, an minus 1, an minus 3, divided by the number above B1, an minus 1. Are we good? Now, B2, this is B1. B2 is gonna be the negative determinant of first two column, first row, first column, an.
It's divided by an minus 1.
Yeah, this one. The number directly above the B. Okay? Now, for B2 is gonna be an minus 1, and then we already considered this line. We move to the next column. An minus 4, an minus 5, divided by this one. Okay? An minus 1. Do you see the trend? So B3 is going to be the minus determinant of this row, okay? And the next row, whatever it is, divided by the left bottom one. Are we good? Now, after this, we have another row, C1, C2, C3. Now, same way that we calculated the B1, we calculate C1. Now, C1 is going to be minus the determinant of these matrix, an minus 1, an minus 3, B1, B2, divided by the left bottom, B1. And the same, you know, the trend, C2, C1, and all the way to the last row. So you have to fill out the table in that manner. Are we good? Any question? Any question? No? Now that we developed the Routh-Hurwitz table, what is the condition that could tell us that if the system is stable or not? We only need to focus on the first column. There are going to be some numbers here. These are constant numbers. If we have the change of sign, so if those numbers in the first column would change the polarity, so we go somewhere, we go plus to minus value, okay, then our system is not stable. If we see no sign, no change in the polarity in the first column, then we have a stable system. Are we good? Now, let's talk about an actual example, this example, and see what's going to happen here. I'm going to replace these with some numbers like 2, 1, 3, 2, and 1. Okay? I don't know what's going to happen. I just wrote these coefficients on top of my head, so I don't know if it's stable or not. I just want to find out. So I am going to I'm going to develop the Routh-Hurwitz table. So this is going to be my Routh-Hurwitz table. So this is S to the power of 4. So we are going to have S4, S3, S2, S, and S to the power of 0. So we are going to have 5 columns. Are we good? Now for S4, we write the coefficients and we skip one place at a time. So it's going to be 2, we skip this one, 3, we skip this one, 1. Are we good? Now, next row, we are going to do that for S3. It's going to be 1, we skip this one, 2, and then we don't have any number. And if we don't have any number, we just simply put 0. Now, what's going to be this value? B1 is going to be the negative determinant of this matrix. So it's going to be 4 minus 3, which is 1. Negative of that is minus 1, divided by the bottom left one. So it's going to be minus 1. Are we good? B2 is going to be 2 times 0, 0, minus 1 is minus 1. There is a minus in front of it, so it's plus 1. Divided by the left bottom one, so it's going to be 1. And we don't have any row here, so there is no number in here.
How did you come up with the first 2 rows again?
The first 2 rows, the first one is S4. So we start with the coefficients of S4, and we skip one at a time. So 2, we skip this one, 3, we skip this one, 1.
Okay.
And then for the next row, we do that for S3. So 1, we skip this one, 2, we skip this one, we don't have any numbers, so 0. Okay? Now, for B1, you have the formula. For C1, which is the next row, again, we're going to use that, so it's going to be 1 plus 2, which is 3. We have a minus sign, minus 3, divided by minus 1, so it's going to be 3. We don't have any row, so this one is 0. And the S0 is going to be minus 3 divided by the minus, multiplied by minus, so it's 3 divided by 3 is 1. Okay? Now we developed our Routh Routh-Hurwitz table. Now, what would be the situation in this example? We go over the first column. This is positive. This is positive. This is negative. This is positive. This is positive. So we have a change of polarity in our first column. So this system is unstable. Are we good? This is how Routh-Hurwitz work. So it doesn't matter what order you have in your function. You just need to simply develop this table and look for the first column to see if there is a change of sign or not. Any question? It's a very easy way. It's just some labor work, which is not hard. It's just multiplication and division. Just remember, one mistake is how you consider which column you consider for B1 and B2. Okay, so B1 is these two, B2 is the first one and the third. And like that goes for B3, B4, all the way to whatever number of B you have. Are we good? Now, there is some special cases that could happen in the Routh-Hurwitz term. We said the criteria for stability and instability is change of the polarity. Okay? But the problem is we don't have only positive and negative number. What is the left from the real numbers that are not positive and negative? Imaginary part also are positive and negative. And we are talking about the real numbers. These are coefficients, so these are always real. Okay? Now, we have three types of real numbers: positive, negative, and neutral. What is that neutral? Zero. So if we have a zero here, we can perform the criteria. Because somewhere in our column we don't know if we change sign or not. Are you good? Is that clear? Now, what happens if we have zeros and how we can deal with that? Two situations could happen that we are going to end up with zeros. Either one of the numbers in first column is zero. This is one situation. Another situation is, and like this is one of them are zero, so one of these are zero, but the rest are positive numbers. So in this row, for example, this one is zero, but this is a positive or negative number. So only one of the elements, the first elements in the row is zero. Is that clear? So the first one is zero and the rest are non-zeros. This is one situation. Another situation, let's say situation A. Another situation is that all of a component in a row are zero. So everything in one row is zero. This is two situations that could happen, okay? And on those situations, we cannot determine if we change polarity or not. Are we good? Okay, now there are two problems. For example, if this one is 0, if we have 0 here, first thing first, we cannot determine the polarity change. And the second problem is that when you wanted to like calculate this one, you have a division by 0. So these are two problems. So you are not going to have these numbers too. And if you don't have these numbers, that means you can't move on to complete the Routh table. Are we good? Is that clear? Now, how we can solve this problem? What we can do is we can run a trick. We can run a trick that we call it an epsilon trick. So we have our Routh table. Let's go for that S for example. We have some numbers, like I'm gonna go simple, okay? So A4, A2, A0, A3, A1, B1, B2, and let's say B1 is 0, C1 doesn't exist, and we are going to end up in a problem. Now what we can do is we can replace this 0 with a very tiny number epsilon. Okay? When this epsilon is very, very tiny, limiting to 0. Are we clear on that? Now, you are going to solve the rest of the table using an epsilon instead of 0. So what's going to happen, for example, here, this one is going to become minus the determinant of this is going to be A3 B2 minus A1 epsilon over epsilon. We don't have anything here, and here we don't have anything here, so 0, not 0. Let's just put no numbers. So now we have our Routh table. Actually, we could have here. Okay, let's talk about it. This is going to be 0, so this is going to be 0 minus B2 times A3 B2 A1 epsilon over minus A1 B2 minus A1 epsilon over epsilon. This is our complete Routh table. Do you know what's happened here? I replaced the 0 with epsilon and used the same equation that we have for B and C to complete the whole table. Are we good? Now, either the epsilon is limiting to 0, so it's a very tiny number. Now, either it goes to 0, that epsilon, this is our 0, that epsilon either goes from the positive number toward epsilon or from negative number toward epsilon. We don't know. So we are going to consider both of the situation. So we are going to first consider the epsilon as a tiny positive number, and we are going to see what's going to happen in the table. Make sense? So this one is positive, these two could be positive or negative. Based on the positive epsilon, we are gonna see what's gonna be the polarity of this number, and same goes for this one. Now we can see if we have a change in a sign or not. And we are gonna do that again for the epsilon when it's negative number. Okay? Now, what's gonna happen? If we have a change of sign in either one of them, that means we don't have a stable system. Is that clear?
Repeat that again.
First, we consider epsilon as a tiny positive number, and we are gonna see if we change polarity here. Then, again, we are gonna consider epsilon as a tiny negative number, and we run the criteria to see if we have a polarity change or not. And if in either of the scenarios we have a change in the polarity, system is not on a stable. Now let's actually run an example to kind of like make it clear. Do you need this table? No? Okay. Now, let's talk about a specific example when our function is s5 plus 2s4 plus 3s3 plus 6s squared plus 5s plus 3. This is our function. We are going to derive our Routh-Hurwitz, so it's going to be s to the power of 5, s to the power of 4, 3, 2, 1, and 0. Now, the first two rows is easy, so it's going to be 1, 3, 1, 3, and 5. And the next one is going to be 2, 6, and 3. Are we good? Now, this is 6 minus 6, so here we are going to have 0. And the rest is going to be 7 over 3. Okay? Let me 7 over 3. Now, since we have a 0, we cannot move forward. So we are going to replace that with an epsilon. And move forward with our situation. Now, to find, let me have a bigger table. It's too crowded. S2, S1, and S0. Now, if you do the determinant based on epsilon, here we are going to have 6 times epsilon minus 7 over epsilon. Okay, and this one, the next one is become 3. 6 epsilon minus 7 over epsilon. And this one is 3. This one become 42 epsilon minus 49 minus 6 epsilon squared over 12 epsilon minus 14, and this one becomes 0. So, 3. You have to like do the calculation. you have to do just the calculation. Are we good so far? Now, what we are going to do? First, we are going to consider epsilon as a positive number, and then epsilon as a negative number. So, if epsilon is positive, first element is positive, second one is positive, third one is positive. The next one, this is 6 times a tiny number minus 7, so it's going to be negative, okay, over a positive number, so it's going to be negative, okay. This one, this is a tiny number, this is a big minus value, this is a tiny positive value, so it's become minus. This is a tiny value, this is a minus 14, so minus over minus is going to be positive, and this one is positive. Okay? Now, let's do that for the negative epsilon. This is positive, this is positive, this is negative. If this one is negative, both of them are negative, and denominator are also negative, so it's going to be positive. This is negative, this is negative, this is positive. Oh, sorry, negative. Okay? Negative, negative, so it's going to be positive, and this one is also positive. Now, if you look at the system, you are going to see we have two change both in positive and negative. What that means? System is unstable. Are we good? Does that make sense what happened here? So this is how we can use the epsilon trick if we have only one zeros in one of the rows. And the 0 should be in the first column. So in the first column we have 0, but the row containing the 0, the rest is non-zero. Are we good? Now, what would happen if all the component in one row is 0? Then what we should do? When this one happens, so when we have a row of 0 in our Routh table, so we have
please explain this part again.
Which one?
The blue circle.
This one? Okay. We consider the epsilon as a tiny positive, and we see what would be the sign of all the first column values.
Yes.
Okay? And these are the signs. See, this is a tiny positive number. This is a positive number with a big negative number. So it's going to be negative. And with the same analogy, we move forward. So for tiny positive epsilon, this is the polarity of the first column. Now, if we have tiny negative value for epsilon, again, we see what's going to be the sign, the polarity of these numbers. If we run the analysis, we are going to see these are the polarities of each of the component in the first column. Now, if we have change of polarity, we said that's a criteria of instability. So this is not a stable. Are we good? Now, what would happen if we have an entire row equal to 0? Okay? When you reach such a point, let's actually do an example. Let's do an example that would be more clear. S5 plus 7 S4 plus 6 S cubed plus 42 S squared plus 8S plus 56. Now, if we have such a situation, the S the Routh table is going to be 1, 6, 8, 7, 42, 56, and then these are going to be 0, 0, 0. And we cannot move from that point. Now, what we are going to do is the first row before the row 0, okay? The first row before the row 0, since this is S3 is 0, the first...
Oh my bad. Oh, why are those zeros on the third?
We use the same formula, so minus the determinant of this divided by 7. So this is 42 minus 42. Okay? Same goes here. 56 minus 56. So it's going to be 0. Okay? So we have entire row as 0. Now, what we are going to do, the trick, is we look at the row before the zeros. So this is S3 is the row of 0. Before that is S4. Okay? And we are going to write it down, these values, as a equation for S. So it's going to be S4. This line is going to be 7 S4 plus 42 S2 plus 56. Okay? Do you get what happened? S4, you skip one power, 42 S squared, you skip another power, 56 S to the power of 0, which is 1. You see what happened? Now, we are going to take a differential. We are going to take a differential from this one. So, if you do the differential, d over ds, you're going to take a differential. This one become 28 S3 plus 84 S, and this one is 0. Are we good? Now, we are going to replace the row 0 with this formula. Make sense? So the coefficients of S3 is 28. So this one become 28. This one is the coefficients of S1. We skip one power. Is going to be 84. So this one become 84. Okay? And when you have this, you are going to move down for the rest of the table. So for example, in this one is going to be 21, 56, 28 over 3, and the last one is 56. Make sense? Can you see what's happened here? Everyone can see? No? Let me move. Can you see now? So what we did is we take a differential from the row before the 0 row, okay, and put the coefficients and derive the 0 row based on that differential. Okay? Now we have complete Routh table. We run the criteria. Here we don't see any sign change. All are positive. That means this system is stable. Does that make sense? Are we good? So this is how we can use the Routh-Hurwitz technique, okay, to analyze the system stability without solving a crazy high order equation for their zeros.
So how do we get the rows after the zero?
Same equation as before. This is the determinant, okay? The determinant of the minus determinant of this divided by 28. Do the calculation. 7 times 84 minus 42 times 28 divided by 28. And there is a minus sign also, so.
Gotcha.
And same as before. The only trick that we did is we replaced the row 0, okay, by the differential of the row before that. Okay? So, the criteria of the Routh-Hurwitz table is no change of polarity in the first column. If we have 1 zeros in one of the components in the column 1, where the rest of the row is non-zeros, we use the epsilon trick, and we have to analyze it for both epsilon positive and epsilon negative. Okay? And if we have an entire row as 0, we use the differential trick. Are we good? Any question about that? So this is how we can analyze the stability of the system. So the definition of the stability and the stability of our system would be analyzed using this trick, which is very easy. Now you can use this for the second order system, okay? Which, to be honest, it doesn't quite hard to do that in regular analysis, but still you can use this and it would work for all the systems. Are we good? Any question? No? Okay, if you don't have any question, that's it for today. And have a good rest of the week.